So in the previous session, we discussed about the matrices and their types, the process of the calculation of inverse, and what is meant by rank of a matrix, and what are the methods to find the rank of a matrix. So do you have any queries with regard to this for the previous session? Then the module of today's session will be, I want to take some problems based on this rank. As one of our friends asked that, how to find the non-singular matrices P and Q such that PAQ is equal to of the form IR00. I want to take the problems on it. Then I want to discuss about the system of equations. However, you have learned it earlier. Again, it will be a refreshing one for you. So there are two types: homogeneous of the form Ax equal to 0 and non-homogeneous of the form Ax equal to b. So we will discuss about the solution methods and approaches. So that would be the module of today's session. Okay. So please take a note of it. Then we will begin our today's session. So if you want anything add, you can add now. Right. So let us begin our today's session. So the first problem is, it was given that capital A is equal to 1, 1, 2, 1, 2, 3, 0, minus 1, minus 1. So our objective is to find two non-singular matrices P and Q such that you are going to get the normal form PAQ equal to IR00. So it is a square matrix. So while considering the identity matrix I, we take the identity matrices of order 3 by 3 only, because it is a square matrix. The given matrix is. So we will write that A is equal to I3 A I3. The prefactor is for rows and the post factor is for columns. So it is nothing but 1, 1, 2, 1, 2, 3, 0, minus 1, minus 1 equals to 1, 0, 0, 0, 1, 0, 0, 0, 1. A will be taken as it is, again 1, 0, 0, 0, 1, 0, 0, 0, 1. Now let us apply the row operations first so that the diagonal entries will be 0. So while applying the row operations, we consider prefactor only on the RHS side. So if we have done R2 tends to R2 minus R1 and subsequently R3 tends to R3 plus R2, then it will become as 1, 1, 2, 0, 1, 1, 0, 0, 0, equals to, here you will get the matrix of the form 1, 0, 0, minus 1, 1, 0, minus 1, 1, 1. A will be taken as it is and it will remain as it is. So please check for that. Now, after doing these row operations, I am going to apply column operations because these two things must be 0. because I want to reduce the given matrix in the form of identity matrix. So I am going to apply C2 tends to C2 minus C1, C3 tends to C3 minus 2C1. So while applying this, it will become as the value 100, 011, 000, and this matrix is same, and you are doing the modifications here. So you will get the matrix as 1 minus 1 minus 1, 1 minus 1 minus 2, and then 0 1 0 0 0 1. Again, to reduce it in the form of IR00, we apply C3 tends to C3 minus C2. So this factor will remain as it is, A will remain as it is. We are going to do the modification only on this right side part. So the resultant will be given as so while doing the iteration procedure, you are saying that you are applying row operations as well as column operations on A, accepted? Right. The row operations are only applied on this part. The column operations are applied only on this part. So we exclude this thing. So while applying row operations, we consider pre-factor only. We exclude post-factor. While applying column operations, we don't bother about the first factor. We do for the post-factor only. Clear? Right. So the pre-factor is for row operations result. The post-factor is for column operations result. So whenever you have a column operation, you are applying only on this part, you are excluding these two. So we take that this is the matrix P and this is the matrix Q. Obviously what happens, if you observe this pattern, P is a lower triangular matrix and Q is a upper triangular matrix. So in one way you can say that you are going to represent the IR00 normal form where P and Q are lower and upper triangular matrices. Always if you consider the determinant for a triangular matrix, the product of the diagonal elements will be the determinant. So this is a non-zero det matrix, so it is a non-singular matrix. It is also a non-singular matrix. That was the whole idea. Okay. Any questions to anyone? It was the easy procedure, right? Let me take one more, then I will conclude problems on it, which gives an idea to you. That's enough. So here if you observe that after doing this, the reduction of the matrix will be in this form. This is the identity matrix. This is a zero matrix. This is a zero matrix. This is a zero matrix. Since it has order 2, so you got the matrix form as I2. Other one is zero matrix of order 2 by 1. You have a zero matrix of order 1 by 2. You have a zero matrix of order 1 by 1. This is the form you got here. So from this you say that rank of the matrix is 2. and this is the required normal form or canonical form you call. Okay. So can I take the other one on this model? Because we have done one problem with the square matrix, let us take one problem on the rectangular matrix. I will give the illustration how to do that, then you have an idea. Right. Shall I continue? So let us take the problem that A is equal to 1, 3, 6, minus 1, then 1, 4, 5, 1, and then 1, 5, 4, 3. Now, if you write A as A is equal to I3, A, I4, because the number of rows are 3, number of columns are 4. Now, on observing this pattern, to get the entries as 0 before the first diagonal element, you need to perform the row operations as R2 tends to R2 minus R1 and R3 tends to R3 minus R1. So, it will be equivalent to A will become as 1, 3, 6 minus 1. Then you have 0, 1 minus 1, 2. Then you have 0, 2, minus 2, 4. And this side, you will have the matrix of the form A will be as it is, I4 will be as it is, because you are writing only row operations, not the column operations. Yes, this method is used to find the rank of the matrix. Actually, while finding the rank of the matrix, we have two procedures applied. One procedure is writing echelon form. By applying only row operations, you are reducing the given matrix in echelon form, so that you will calculate how many number of non-zero rows are there, which is nothing but rank of the matrix. The second one is nothing but normal form or canonical form. In this, we will represent the matrix in the form of IR00. So from this, R indicates the rank of the matrix. So you are reducing the given matrix in the form of an identity matrix of order R and the remaining are 0 matrices. Here we are applying both row and column operations. And one of this useful thing is, you are going to find two non-singular matrices, P and Q, such that it will be reduced in the form of IR00. Please understand one thing, that if the question is not mentioned that find non-singular matrices, then we simply consider A. We will apply row as well as column operations, and we will make A as equivalent to IR00. We don't bother about P and Q matrices. Whenever P and Q are asked, then only we will consider pre-factor and post-factor. Otherwise, we simply apply row operations as well as column operations, and we reduce A in the form of IR00. That's all. It is based on the question pattern. Okay? Any questions, please? So is that clear? Any other doubts? Right. So after applying the row operations, it is going to come as 1, 0, 0, minus 1, 1, 0, and you have minus 1, 0, 1. So you can observe that while applying the row operations, I consider the prefactor only, post factor will be taken as it is. Now, I want to take one more operation, R3 tends to R3 minus 2R2, making this value as 0. Then it will be equivalent to 1, 3, 6 minus 1, 0, 1 minus 1, 2, 0, 0, 0, 0 equals to, here we will get the matrix as 1, 0, 0 minus 1, 1, 0, and the last row will be termed as 1 minus 2, 1. So once we have done that, the elements below the first diagonal are 0, the elements below the second diagonal are 0, then nothing is there to make 0 below the diagonal elements. Now you are going to apply the column operations. So the process while applying the row operation is, we first take the first diagonal element, then make the values as 0 before it or below it. Then we consider the second diagonal element, then we check whether the below value is 0 or we will make it as 0. So once we have finished with this type of pattern, then we start doing with the column operations. Now you are going to apply the column operations as C2 tends to C2 minus 3C1 because this is 3. C3 tends to C3 minus 6C1. C4 tends to C4 plus C1. Right? So then it will become as 1, 0, 0, 0. Then you have 0, 1 minus 1, 2. Already this is 0. And this factor will remain as it is. This is A. And for I4, you are going to get a new matrix as 1 minus 3 minus 6, 1, 0, 1, 0, 0, 0, 0, 1, 0. So that was the post factor. Again, you need to make these two values 0. It is possible using this number. So C3 tends to C3 plus C2 and C4 tends to C4 plus C2. I mean C4 minus 2C2. Then it will come as 1, 0, 0, 0, 0, 1, 0, 0. And this factor will be as it is, this will be A, and you will get a new matrix here. So that matrix will be in the form of that was the new matrix. So in this context, we need to understand that whenever the non-singular matrices P and Q are asked to be found, then in such case only we use this procedure. Otherwise, whatever the operations I have applied are written now, row operations and column operations, we simply apply on the LHS side. There will be no RHS at all. There is no need to find P and Q matrices. So we simply consider the given matrix A, we apply row operations as well as column operations and reduce in the form of IR00. So here if you observe that this is the form of IR00. So I2, 0 matrix of order 2 by 2, 0 matrix of order 1 by 2, 0 matrix of order 1 by 2. This is the thing you got here. So on observing the order of identity matrix, we can say that rank of the given matrix is 2. Okay. So I have taken these two examples based on the rectangular matrix as well as square matrix so that you will get the idea how to find the rank as well as how to determine the non-singular matrices. So if you have one doubt that how to apply echelon form, I will take the echelon form also. Do you require a problem based on echelon form or not required? Right? So if you have noted this, I will erase. So I want to take one more problem on echelon form for finding rank of the matrix. After noting, you please inform. So did you get any confusion while applying this procedure, anyone? Or is that clear? Fine. Let us take the problem that -1, -3, 3, -1, 1, 1, -1, 0, 2, -5, 2, -3, -1, 1, 0, 1. Suppose this is our matrix A. I want to find the rank of the matrix using echelon form. So here, one interesting thing we need to observe is generally while applying the row operations, if for any row the first element is 1, then we interchange the first row with that, because while applying the row operations it is convenient to perform the operations. Since it is -1, it is okay. Otherwise we will do the thing that, let me say, suppose I want to interchange these two, R2 and R1 are interchanged. So it will be equivalent to 1, 1, -1, 0, -1, -3, 3, -1, 2, -5, 2, -3, -1, 1, 0, 1. If 1 is not there, it is okay. We do the procedure as it is. Otherwise, we will interchange so that if 1 is there in the first position, it is convenient to apply the row operations. So to make it 0, we do that R2 tends to R2 plus R1. So R3 tends to R3 minus 2 R1, and R4 tends to R4 plus R1. So because using the first row only, we do all the elements before it has 0. So it will be equivalent to, first row remains unchanged on adding 0, -2, 2, -1. Here it will be 0. R3 tends to R3 minus 2 R1. So -7. 4, -3. Then R4 plus R1, it will be 0, 2, -1, 1. Now what happens again, using this element, you are going to make these two values as 0. So you can say that R3 tends to -2 R3 plus 7 R2, and R4 tends to R4 plus R2. Then it will be equal to 1, 1, -1, 0, 0, -2, 2, -1. Here you will get 0, 0, 1, 0. And you are going to get the values here. You are going to simplify that. -14 plus 14, 0 here. So -8 plus 14. So +6. Again +6 -7 -1. So again, using this, you are going to make this value as 0. Now what happens? So do you accept for these values? If you did anything wrong with regard to row operations, you can correct me. So how do we justify that it is in the echelon form? Because all the values below the diagonal entries must be 0. So these values are 0, these values are 0, these values are 0. However, if you get any 0 row, that will be in the end. How many 0 rows you will get? They should be at the end. So above the criteria must be the elements before the diagonal entries must be 0. So it satisfies the echelon form. Since you didn't get any row completely as 0, so all the 4 rows will be considered as non-zero rows. So the rank of the matrix is nothing but 4. Okay. So we will count how many number of non-zero rows are there. Based on that, we say that the rank of the matrix is this. So for this problem, the rank is 4. So is that clear, or any doubts to anyone? Right. Now the advantage of row operations is, by only using row operations, we are able to determine the rank of a matrix. That we call it as the Gauss-Jordan method. So in Gauss-Jordan method, we determine the inverse of a matrix by means of row operations. So let us take one problem, then you will get an idea. So let us take the matrix as 1, 1, 3, 1, 3, minus 3, and then minus 2, minus 4, minus 4. This is my matrix A. Now, I want to apply only row operations on this matrix, and I need to get the inverse of A. So for this, generally one procedure is, we will say it is equivalent to the identity matrix into A. So I will apply exclusively row operations on this, so that the given matrix will be reduced in the form of identity. I will get a new matrix here. So for convenience, without having any ambiguity, I am going to consider the augmented matrix for applying Gauss-Jordan method. So I will consider A by I. So I will get the matrix like this. So I am going to apply row operations here and here, same operations. It will be turned into identity matrix. Here you will get a new matrix. So how to say that? The diagonal values must be 0 first. So R2 tends to R2 minus R1, R3 tends to R3 plus 2R1. I want to distort the matrices. Then I will do that. R2 tends to 1 by 2 R2, and R3 tends to 1 by 3 1 by 2 R2. Because since it is only based on applying row operations, I am excluding this part. Writing each and every row operation and doing the corresponding matrix is somewhat time taking. So straight away I am listing out the row operations and how the necessary change is going to take place. So then you will get the matrix in the form as 0, 1, 3, 0, 1, minus 3, 0, minus 1, 1, oblique. So this will be the resultant matrix. So please check them once. Then I will write the further operations, if you agree with that result. So did you feel any difficulty in applying these row operations? Or the method is clear for you? Please specify. So are you comfortable in getting the result? Right. Now I am going to write the subsequent row operations. So once we have done with this, based on this diagonal element, I am going to make these two as 0. So I am making R1 this part as 0 using this, R3 this part as 0 using this. So the respective operations are given by R1 tends to R1 minus R2 and R3 tends to R3 plus R2. It will be equivalent to 1, 0, 6, 0, 1 minus 3, 0, 0 minus 2, oblique. You will get a new matrix as so now I am going to apply R3 tends to minus 1 by 2 R3. Why? Because since minus 2 is there, if I divide with minus 2, it will become 1. So that I need to make these two values as 0, because my intention is I want to make the given matrix A to be identity matrix. So for this, these two values must be 1. So if 1 is there, I need to perform the operations in a better way. Obviously, this must be 1 because I need to get the identity matrix. So later I will perform R1 tends to R1 minus 6 R3 and R2 tends to R2 plus 3 R3. So the final result will be like this. Oblique so the new matrix which you have obtained there is nothing but the inverse of the given matrix. That is A inverse. Now the difficult part here is finding the respective row operations to convert it into identity matrix is easy. But the thing is, while performing the operations on the other side, on the identity matrix part, you will get fractions of this model. So for the calculation part, it takes time for you without having a proper practice. That was the only difficulty in this Gauss-Jordan method for finding A inverse. Okay, so please take a note of it. Then we will move to the new concept, that is system of linear equations. If you have any other queries with regard to this, you can ask. Anybody? So do you need any elaboration for these procedures, or is this sufficient? So coming to system of linear equations, suppose we have m number of equations and n number of variables. Then you will get a m by n matrix if you represent the coefficients in those equations in the form of a matrix. Now usually for solving the system of linear equations, in general we consider the square matrices, and majority of the problems are posed on square matrices only, not on the rectangular matrices. However, for some problems we deal with rectangular matrices too. That is not an issue. So the main part of system of equations will be classified into two types: homogeneous system and a non-homogeneous system. So let us take a small example that which is already known to you. Say 2x plus 3y is equal to 0 and x minus 4y is equal to 0. You can take one more thing. So here you will have a system of equations having two variables. Since the right side is 0, we call it as a homogeneous system. So if you consider the system in the form of a matrix, you will get like this: 2, 3, 1, minus 4, 1, 5 of xy is equal to 0, 0. This type of representation we usually denote with ax equal to 0. Now, coming to the solution part, whenever you have a homogeneous system given, we represent that system into equivalent matrix system like this, and we apply row operations on this coefficient matrix, and we will find its rank. Suppose if the coefficient matrix you have taken as A and you found the rank of A is equal to R. Now the solution is determined as if rank of A is equal to n, the number of variables. Rank is equal to number of variables. Then we say that the given system has only trivial solution, that is 0, 0 is the only solution for it. If rank of A is less than number of variables, if number of variables are n, rank is R, you consider the difference n minus R. So the system will have n minus R independent solutions, and you will get infinite solutions in this case. So we say that the homogeneous system has only two types of solution: one, trivial solution; second, infinite solutions. So in the infinite solutions case, you will get how many independent solutions are there. That is, we are going to calculate. So this is all about the homogeneous system. Any questions? Right. So coming to the non-homogeneous part, we consider the augmented matrix A by B. It means, let us take that the system is given as 2x plus 3y is equal to 6, x minus 4y is equal to 0, x plus 5y is equal to 9. So we will have a system of the form 6, 0, 9. So we call it as the matrix representation Ax equal to B. A stands for the coefficient matrix, X stands for the variable matrix, and B stands for the right side constant matrix. So the augmented matrix will be considered as 2, 3, 1, minus 4, 1, 5, oblique 6, 0, 9. Now we apply the same row operations on either of the parts. So if you consider only this part, this is A. If you consider the entire part, it is B. I mean A by B. So we consider rank of A also rank of A by B. Whenever these two values are equal, rank of A and rank of A by B, then only the system will possess a solution. And we say that the given system is consistent. So a system which will possess a solution, we call it as a consistent solution, consistent system. So whenever rank of A is equal to rank of A by B, we call it as a consistent system and it will possess a solution. If it is not equal, then the system is inconsistent, it has no solution, right? So consider the case rank of A is equal to rank of A by B. If this value is equal to number of variables, then we say that the system will have only unique solution. That means x, y, z, you will find only one solution for it. Exactly one solution will be there for the given system. If rank of A is equal to rank of A by B and it is less than number of variables, in such case you will get infinite number of solutions for the given system, and among which the number of independent solutions are given by n minus r. N stands for number of variables, R stands for rank of the matrix. So this is the pattern for solving non-homogeneous system. Okay, so please take a note of that. Is this formula known to you or not? Fine. So shall I erase this? Okay. So let us take the problem that x plus y plus z equal to 4, 2x plus 5y minus 2z equal to 3, x plus 7y minus 7z is equal to 5. Now the thing is, we are going to verify whether the system is consistent or not. If it is consistent, then we are going to find its solution. Since it is a non-homogeneous system, let us write the corresponding augmented matrix straight away. So first you are going to write the equivalent matrix form Ax equal to B, and you consider the augmented matrix or improved matrix, we can call A oblique B equals to 1, 1, 1, 2, 5 minus 2, 1, 7 minus 7, 4, 3, 5. Now let us apply the respective row operations here. So R2 tends to R2 minus 2 R1, and R3 tends to R3 minus R1. So it will be equivalent to 1, 1, 1, 0, 1, minus 4, 0, 6, minus 8, oblique 4, and this will be 1. R2 tends to R2 minus 2 R1, 4 minus 5, 1. Accepted? And you will say R2 minus 2 R, it will be 3. Right? Agreed all? So while applying the row operations, we need to understand that we are applying the row operations to get the echelon form and the coefficient matrix. So after having zeros below the first diagonal element, you have to make this value as 0. So R3 tends to R3 minus 2 R2. It will be equal to 1, 1, 1, 0, 3 minus 4, 0, 0, and it will become 0, oblique 4 minus 5, and you will get the value as 11. Now, if you consider the ranks, rank of A is equal to 2, because this is the part I am considering. It has only two non-zero rows, first row and second row, third row has become 0. So the rank of A is equal to 2. If you consider rank of A by B, it is 3, because while considering A by B, we will take the whole part. So all the three rows are non-zero because this part is not 0. So hence rank of A by B is equal to 3. Since these values are unequal, the given system is inconsistent, so it has no solution. Okay? Clear? Any questions? So please take a note of that, then we will discuss about other methods. Actually, without having augmented matrix also, we can solve the non-homogeneous system of linear equations. These methods are already known to you in the earlier classes like +2 or BTech level. Let us reconsider them. So whenever system of linear equations in the non-homogeneous form is given, so the respective methods to solve is Cramer's rule, also known as method of determinants. And secondly, matrix inversion method. And third, Gauss elimination method. Have you known these methods? Are not known? So usually we apply these methods for the square matrices. Whenever the coefficient matrix is a square matrix on the left side, we will apply these methods, which is convenient for us to solve. Can you recollect those concepts? Otherwise, I will give you a small illustration over them. How we are going to work with these methods. Right. So do you require a small introduction over these methods? What we are doing actually there? Right. So let me start with 2 by 2. That is somewhat convenient, apart from taking 3 by 3, which saves our time. Or we can take 3 by 3 as well. First of all, we should know whether the given system will possess a solution or not. So for the application of these methods, the determinant of the coefficient matrix must be not equal to 0. Then only it is applicable. It means the system will possess a unique solution. So if you write the matrix in Ax equal to B form, so 3, 4, 5, 1, minus 1, 1, 1, 1, 2. So we consider determinant of A, it must be not equal to 0 first. So in this case, let us assume that determinant of A is not equal to 0. So the given coefficient matrix is singular, hence the system will possess a unique solution. Now what happens? The value of determinant of A we use with the symbol delta. So first we are dealing with the Cramer's rule, and we are describing about the procedure of Cramer's rule. So we calculate the determinant of A and we use the symbol delta for it. And we are going to find subsequently 3 more determinants, how they are going to be evaluated. In this coefficient matrix, you remove the first column with the right side constraint matrix. So 2, 1, 16, 4, minus 1, 1, 5, 1, 2, we will take like this. So for this matrix, we calculate the determinant, we indicate with the symbol delta 1. So delta 1 says that I have removed the first column, I have replaced the first column with the constant matrix, and I have evaluated the determinant. That is the meaning of delta 1. Similarly, we calculate the other determinants delta 2 and delta 3. So first column will be taken as it is, only second column will be replaced, calculate the det. For delta 3, first and second columns are taken as it is, only third column is replaced with the constant matrix, we evaluate the det. So after calculating these 3 more determinants, the values of x, y, z will be taken as x is equal to delta 1 by delta, y is equal to delta 2 by delta, and z is equal to delta 3 by delta. That's why this method we call it as the method of determinants. So also known as Cramer's rule. So the main drawback of this method is, right? So delta 2 is nothing but 3, 1, minus 1, 3, 1, 1, 2, 1, 16, 5, 1, 2. So in this, first and third are taken as it is, only second is replaced. So delta 2 indicates that second column is replaced with the constraint column. Right. Similarly, delta 3 is nothing but third column is replaced with the constraints column. First and 2 are taken as it is. So delta 3, if you want to write, determinant of 3, 1, 1, 4, minus 1, 1, 5, 1, 2 is replaced with 2, 1, 16, and you evaluate the debt. So what is the drawback of this method? It is good for the application of 2 by 2 and 3 by 3 matrices, as and when you go with 4 by 4, 5 by 5, it will be very difficult to calculate the debt. So this method is not at all useful. Do you agree? So the drawback of Cramer's rule is it will be good for 2 by 2 and 3 by 3 matrix system, not for the higher order matrices. Any questions for anybody with regard to Cramer's rule? Right. Now let us go with the second method, that is matrix inversion method, which is already known to you. Now for every method what you are applying, the basic criteria is determinant of A must be not equal to 0. Then only you are going to apply one of these methods as per the question posed. So here, if you talk about matrix inversion method, so once calculating determinant of A, since you got that Ax is equal to B, if you multiply both sides with A inverse, you will get X is equal to A inverse into B. So for A inverse, we will use the formula 1 by determinant of A into adjoint A. So it is nothing but, suppose, can you say the determinant of this matrix, what it will be? The given matrix 3, 4, 5, 1 minus 1, 1, 1, 2, 3. So it is nothing but 1 by 3 into adjoint A of A you are going to find, and B is nothing but 2, 1, 16. So this is the 3 by 3 matrix. Now what happens on simplification, you will get 1 by 3 into 3 numbers. So you will get XYZ. So here X is nothing but XYZ. I think you can recollect this procedure. You have done it already. Say. So can you recollect how to calculate adjoint of A, or you want me a small illustration over that? All of you. Is that required or not required? Can I go for the procedure how to find adjoint of A, or not required? Fine. Now the difficulty here is, if the problem is asked that using Gauss-Jordan method solve the system of equations, the non-homogeneous. So apart from calculating X is equal to A inverse into B, we calculate A inverse with the formula adjoint of A by det A. So here also X is nothing but A inverse into B, but for the calculation of A inverse, we have done a previous problem using row operations only. We have computed A inverse, right? So A inverse is computed using only row operations. So multiplying these two, you will get X automatically. So for matrix inversion method, in the calculation of A inverse, two things are there. But some others says that without applying row operations, A inverse is nothing but adjoint of A by det A. So for Gauss-Jordan method, you can do like that. So actually, in order to get A inverse, Gauss-Jordan method means we apply row operations only. But many of the students follow that A inverse is nothing but adjoint A by det A. We follow and we will solve, and marks will be awarded accordingly. Okay. So this is the procedure for matrix inversion method. And let us go with the Gauss elimination method. Shall I continue? Any questions? So for Gauss elimination method, we consider the augmented matrix A by B. As per the previous case, what we have considered now. So 3, 4, 5, oblique 2, 1, 16, 1, minus 1, 1, 1, 1, 2. This is our augmented matrix. Now, after applying the row operations, we are going to make this part A into upper triangular matrices. We are just applying the row operations to get echelon form. Automatically it will be in the form of upper triangular matrix. So by using back substitution, you will get the values of x, y, z. So let us do it for now. So let us interchange these two for convenience. R2 tends to R2 if and only if R1. So equivalent to 1 minus 1, 1, oblique 1, 3, 4, 5, 1, 1, 2, 2 and 16. So R2 tends to R2 minus 3 R1 and R3 tends to R3 minus R1. So equivalent to 1 minus 1, 1, 1, 0, 0. So R2 minus 3 R1. So this will be 7, 2, 2, 1, and then you have R2 minus 3 R1. Again, you are going to make the element here as 0. So you have to do R3 tends to 7 R3 minus 2 R2. Then this will be equivalent to 1 minus 1, 1, 1, minus 1, 0, 7, 2, 0, 0. Three, and you have here am I correct? Right. So we will write the respective equations as x minus y plus z is equal to 1, 7y plus 2z is equal to minus 1, and 3z is equal to 107. I think all of you agree with my computational values. I hope so. So am I correct here? Fine. So from this, back substitution is starting from the last equation to first we go. So z is equal to 107 by 3, and substituting z here you will get y, substituting y and z here you will get x. So this is Gauss elimination method. But here we need to consider one thing, that majority of the students will write the row operations like this. For Gauss elimination, it is also known as the pivot method. It means that while applying a row operation, right, always we will use the pivot. What is meant by pivot? Now, if you observe that, if you want to make this value as 0, you have applied the operation as R3 tends to 7R3 minus 2R2. But actually, in Gauss elimination method, you need to write the operation as R3 tends to R3 minus 2 by 7 R2. So what I am doing actually, whatever the diagonal element is there, with the diagonal element, you are dividing all the bottom values. So here, since this is the first diagonal element, if you want to correctly write the row operations using the pivot element method. So here I will make space here. So first I have interchanged it. It is okay. Now this part I want to make 0. So R2 tends to R2 minus 3 by 1 R1, because the diagonal element is 1. With this diagonal element I am dividing this. Since 3 by 1 is nothing but 3, I am writing 3R1 as it is. Similarly, R3 tends to R3 minus 1 by 1 R1. Here the element is 1, diagonal element is 1. With this one you are going to divide, so 1 by 1 R1. So actually there is no problem generally for writing the first set of row operations. So for writing the second set of row operations, we must take care of, because you are using a diagonal element as the pivot. So with this 7, you are going to divide all the bottom values. That's why R3 will be written as R3 minus 2 by 7 R2. So respective changes will be taking place here. There will be no change in the answer. The back substitution will be done as it is. So the actual Gauss elimination method we need to consider like this. You should write the operations so that in this coefficient as well as here you will get fractions. Some elements will be in the form P by Q. So back substitution is common, everything is common, procedure is common, no change at all. But generally, for the computation convenience, we will write the row operations in this model and we will solve the system. Okay? So please take a difference between these two. If the question is asked that using Gauss elimination method solve, both are right, please understand. If the question is exactly posed that using Gauss elimination method or pivot element method solve, you should write this type of row operations only. This method is wrong. Whatever the row operation you apply, answer will be unique. There will be no change in the operation. I mean the final answer. But there is a change in the computation procedure. Right? So the actual thing is you are dividing all the below elements of the diagonal element with the diagonal entry. Suppose if you are a computer science student, please understand, if you are a computer science student, if you are writing a computer programming for the calculation of this part, how do we write? Because you don't know what are the elements there, right? So you cannot always judge this minus this. That is practically not possible to make it 0. So the actual Gauss elimination method is nothing but this, the pivot element method. If the question is asked that simply solve the system of equations, find its solution, whatever the row operation you write, that is accepted, no doubt at all. If the word is particularly given using Gauss elimination method, you should write the operation on that way only. So may I know how many of you are the computer science students? Let me say, because if you want to write a computer programming, what we are going to do? We check whether the diagonal element is 0 or non-zero. So first we do like this. So if it is non-zero, then division with this element is possible since it is A22. So you are going to say that R3 tends to R3 minus what the element is there divided with A22 into R2. R4 tends to R4 minus the element what you are taking. Everything is going to be written like this. So computer programming or computer coding is easy. So this is the actual Gauss elimination method, please understand. Since you are taking third row second element, so R3 tends to R3 minus R32 by A22 into R2. R4 tends to R42 by A22 into R2. And R5 tends to R5 minus R52 by A22 into R2. Please understand, in this way coding is possible. If you don't know what are the elements is there, what element you are going to make that the subsequent values are 0, it is not practically correct unless a problem is given to you. If the values are unknown, you cannot predict a coding for it. So Gauss elimination is good for coding, computer science coding, right? So usually for Gauss elimination method, we take the pivot. The pivot is nothing but the diagonal entry. Now what happens if the diagonal entry is 0? We simply exchange the rows so that that corresponding diagonal entry must be non-zero, and we do the as-is procedure. Clear? That's it. Suppose I have taken a 4x4 matrix. So on applying the row operations, I get the values like this. This is 0. And this also happened as 0, element. So this is 0. This is some value happened here. Element, again 0, element. Since this is 0, you simply interchange these two so that this element will be non-zero. We do the procedure as it is, no change at all. That is the technique in Gauss elimination method. Okay? Is it clear for you, the approach? But generally question will not be asked that using the pivot solve. They won't give such type of question. So with the regular pattern, how we are going to write a row operations, we will write it normally and we will solve the problem. No difference at all. That's it. If the problem clearly mentioned that using pivot, you should write in this model only. That is the only correct way. Okay. So this is about solving the system of equations. So let us take one more problem, then we will wind up our discussion. I think this problem is given in the previous year papers. Let us take for that. So are you ready? Fine. The question is, for what values of lambda and mu the given system has no solution, unique solution, and infinite number of solutions. And the equations are given as x plus y plus z equal to 6, x plus 2y plus 3z is equal to 10, x plus 2y plus lambda z equal to mu. So in UPSC you can expect similar kind of question. I think this question was asked twice. After noting, please inform. So whenever you consider a non-homogeneous system, it will contain no solution, unique solution, and infinite number of solutions. Are you noted this? Now let us write the augmented matrix first. So in the exam, you need to write the equivalent matrix pattern as Ax equal to B. Then you need to mention this is the augmented matrix A by B, and this is equal to 1, 1, 1, 1, 2, 3, 1, 2, lambda oblique 6, 10, and mu. So we will apply row operations as these. Please understand, here we are not applying the Gauss elimination pivot method. We are simply applying the row operations at our convenience, because in the question it is asked to determine the lambda and mu to get the required solution. Based on Gauss elimination, he didn't mention. So you can apply any kind of row operations here to get the required answer. So R2 tends to R2 minus R1, R3 tends to R3 minus R1. So equal to 1, 1, 1, 6, 0, 1, 2, 4, 0, 1, lambda minus 1, mu minus 6. So to reduce that into echelon form, again, the value below the second diagonal element must be 0. So we should apply the operation as R3 tends to R3 minus R2. So this will be equals to 1, 1, 1, 0, 1, 2, 0, 0, lambda minus 3 oblique 6, 4, mu minus 10. Please check for it. So do you accept for it the values? So if you want to check for unique solution, what is the criteria? Rank of A, rank of A by B, and number of variables all must be equal. Then you will get unique solution. So rank of A must be 3, rank of A by B must be 3, and here you have number of variables are 3. So now what happens if lambda is any number except 3? Then what happens? This will be non-zero. So if lambda is not equal to 3, then rank of A is equal to 3. You forget about this portion. So whatever the number you substitute here, you may get 0 or non-zero, that doesn't matter. Since you have a non-zero entry, rank of A by B is nothing but 3. Accepted? Are you getting the logic or not? So if lambda is not equal to 3, mu is any real number, then rank of A is equal to 3, rank of A by B is equal to 3, which is equal to number of variables. So the given system is consistent and it has unique solution. That was the conclusion for this portion. So after the reduction into the above form, we put a side heading, unique solution. And here we mentioned that if lambda is not equal to 3 and mu is any real number, then rank of A by B equal to number of variables that equal to 3. So the given system is consistent and it has unique solution. Now coming for no solution case, no solution appears only when rank of A is not equal to rank of A by B. So that is possible whenever this entry is 0 and this entry is non-zero. So we have to mention that if lambda is equal to 3 and mu is not equal to 10, then rank of A is equal to 2 and rank of A by B is equal to 3. So the given system has no solution because it is inconsistent, as rank of A is not equal to rank of A by B. Okay? Is that clear or not? Because if you have a doubt, if you substitute the values, it will come like this: 1, 1, 1, 0, 1, 2, 0, 0, 0, oblique 6, 4, you will get some number here. So rank of A is equal to 2, rank of A by B is equal to 3. If you take this type of pattern here, that system will be reduced into this form. Agreed? Any doubts to anyone? Fine. And coming to the part, opposite possible means if you say that lambda is not equal to 3 and mu is equal to 10, then what happens? Is that your question? So if you say that lambda is not equal to 3 and mu is equal to 10, since lambda is not equal to 3, you will get some number here and this will be the 0. Agreed? Yes or no? So here rank of A is 3. Rank of A baby is also 3. Please understand, A means you are considering only this part. A baby means you are considering this part. Even though this is 0, this entire row is not completely 0 because one value is presented here. So both are equal. In that case, you have unique solution. It is consistent. So if you want to say that always it has no solution, the fundamental thing is this part must be completely 0. Here you should get a non-zero entry. Okay? Then only rank of A baby both will be unequal. It will be inconsistent. Any questions to anyone? Fine. And for the last part, infinite number of solutions, it is possible only when rank of A baby both are equal and they must be less than number of variables. So if I say that if lambda is equal to 3, mu is equal to 10, then the given system will be in the form the last row will become completely 0. So you have rank of A is equal to 2. If you forget this portion, rank of A is equal to 2. Rank of A baby, it is also equal to 2 because only 2 non-zero rows are there. The last row has become completely 0. So rank of A is equal to rank of A baby, which is less than number of variables. Therefore, given system is consistent, it has infinite number of solutions. So if you observe the problem perspective, you are determining the values of lambda and mu so that the system has unique solution, no solution, and infinite number of solutions. And please understand that you are not determining the solution here because the problem is not at all asked so. If at all it is asked, then you need to evaluate the infinite number of cases. Okay? Because you don't know what is lambda and mu in the previous cases. That's the thing. You need to evaluate the infinite number of cases. Clear? So do you have any doubts with regard to the discussion for this problem? The approach, how to find no solution, unique solution, and infinite solution cases. Then let us wind up our discussion here. So I am going to resume our sessions from Saturday onwards as usual. Tomorrow and day after tomorrow, we are taking holidays for the festival, right? Thanks to all. And if you have any other queries, you can ask. I think an assignment is posted on read analysis in the group. Did you get that? Or not? Right, then I will ask them to prepare it again. I have given the questions already with regard to improper integrals and Riemann integration, etc. If possible, I want to give one more assignments comprising limits and derivative part. Then it will give the good idea of our complete reanalysis. Then after completing one or two sessions over this linear algebra, I will give one more assignment. Taking all these rank Hermitians, Q Hermitians, symmetric maxes, etc., etc., I will give one assignment, which will enhance your knowledge. So thanks to all. If you want to add something, you can add. Otherwise, let us wind up our session here. Right. So we will meet on Saturday. Thanks to all.